Hi everyone. This is our overview of the electrochemistry unit. Something really fundamental about the unit is this mnemonic up here that Leo's a jerk. It's a little bit of a strange spelling for jerk, chemistry spelling, G-E-R-C, but it stands for loss of electrons is oxidation, that happens at the anode. The gain of electrons is reduction, that happens at the cathode. It's the reducing agent that's oxidized at the anode. It's the oxidizing agent that's reduced at the cathode. We can use oxidation numbers to identify oxidation. If the oxidation number goes up, that's a sign we had oxidation. It was the reducing agent. If the oxidation number goes down, that's a sign we had reduction, and it was the oxidizing agent. We can answer all kinds of questions just using those ideas. Building off of that was the idea of spontaneity. When we use the table in the data booklet, if the oxidizing agent is higher than the reducing agent, it's going to give us a spontaneous reaction. But if it's the other way around, if the oxidizing agent is lower down on the table than the reducing agent, we're going to have a non-spontaneous reaction. The ideas of spontaneity can also pop up in a couple of different ways. We can get asked questions about a container. Okay? A container should not react with its contents, so we're looking for a non-spontaneous reaction there. We can use spontaneity rules to generate a table in a couple of different ways, from a list of reactions or a table of reactions. We could do table building. Okay? This is the layout of the table that's in the data booklet. Oxidizing agents on the left, reducing agents on the right. The strongest oxidizing agent at the top, getting weaker as we go down. The strongest reducing agent at the bottom on the right, getting weaker as we go up. Couple of things. Some oxidizing and reducing agents are a combination of chemicals. We're really going to have to watch out for a combination with water or hydrogen ions, probably the most common, even hydroxide. Watch out for those double agents, chemicals that are both oxidizing and reducing agents, like water or tin 2 ions or iron 2 ions. Watch out for those. They show up on both sides of this table. We're going to use the table and our spontaneity rules also with what's called predicting redox reactions. We're going to use a 5-step method to do that. Make a list of all of the substances that are present. Don't forget to put water in your list probably. Dissociate ionic compounds. Keep molecular compounds together. Watch out for if a question says acidified, put hydrogen ions in your list. If it's basic, put hydroxide ions in your list. Make a list. Use the data booklet table like crazy to label all of the possible oxidizing and reducing agents. Again, watch those combination agents, watch those double agents as we're doing our labeling. Identify the strongest oxidizing agent, it's the one that's highest up, and then literally copy the half reaction from your table. The strongest reducing agent is the one that's lowest down on the right. Here we're going to have to reverse the half reaction before we copy it. We're going to balance the electrons. The electrons lost and gained have to equal each other. We're going to multiply the half reactions to get the electrons to balance. Be on the watch for any extra canceling or grouping. Remember, the same chemical on opposite sides cancel. We might even get partial canceling, but the same chemical on the same side groups together. It's very similar to what we encountered with additivity way back in thermochem. It's easy to forget the last step because it's a pretty long process. At the end, we want to say, is the oxidizing agent higher or lower than the reducing agent? Say if the reaction is spontaneous or not. Once we have generated our equation, our reaction, the net ionic equation, we might have to do some stoichiometry to it, especially titration style questions. Okay. Once we have our reaction, maybe it's given to us, maybe we had to go all the way through the 5-step method, generate our reaction, we're going to find moles. The nicest kind of question will tell us moles, so we could find it by reading. It's unlikely we're going to have to do mass over molar mass at this point, probably doing concentration times volume, multiply by the mole ratio, R over G. Whatever we're multiplying the half reactions by, those values are what we'll use for the ratio. And finally, solve. We might be looking for the moles, the mass, the volume, or the concentration. Okay. More often than not, we're going to find the concentration because a lot of the time in this unit, this redox stoichiometry is connected to titrations. After all that, we moved on to oxidation numbers. We talked about how to assign oxidation numbers. Elements are 0, hydrogen is +1, hydrides are an exception, -1, oxygen's -2, an exception is peroxides, which are a -1. Simple ions, if we can actually see the charge of a simple cation or anion, the oxidation number matches the charge. Finally, the total of all of the oxidation numbers in a polyatomic ion or in a compound all adds up to the charge. We can use oxidation numbers for a whole bunch of things. I already mentioned we're able to identify a reducing agent that got oxidized if the oxidation number goes up. We're able to identify an oxidizing agent that got reduced if the oxidation number goes down during the course of a reaction. We can use oxidation numbers to balance chemical reactions. If we have a net ionic equation that's not balanced, we can assign oxidation numbers to every substance in the reaction. Look for the change. Watch out for subscripts. Balance the electrons. Take those multiplication factors and use them as the coefficients. Balance by inspection. Don't forget, we might have to add water to one side or the other to get the oxygens to balance. And we're going to introduce hydrogen ions to get the hydrogens to balance. That doesn't necessarily happen every time, but it's really common. If we have a balanced equation, we might be asked what's the sum of the coefficients, something like that. Finally, we can use oxidation numbers to identify if we have a redox reaction. It's a really important kind of question. Hey, is this reaction a redox reaction? Assign oxidation numbers. Something goes up and something goes down. The oxidation numbers go up and down. We had oxidation and reduction. We have a redox reaction. Finally, we can use oxidation numbers to identify disproportionation. It's when the same substance is oxidized and reduced at once. The same substance has its oxidation number go up and down. Disproportionation. From there, we moved on to Voltaic cells. Okay. Two very common types of diagrams for Voltaic cells. One uses a salt bridge, the other a porous cup. The telltale sign that we're looking at a diagram of a Voltaic cell is there's a voltmeter, a circle with a V in it right at the top of the diagram. There are all other types of diagrams we might get asked to interpret, but two really common ones. These represent batteries. Voltaic cells are batteries. Any type of battery you could imagine in an automobile, in your cell phone, in a remote control, those are all Voltaic cells. They produce a voltage. They give off electricity, batteries. They're going to convert chemical energy into electrical energy. Here, oxidation happens at the anode, reduction happens at the cathode, where the anode is the negative half cell, the cathode is the positive half cell. It's a very useful acronym. Leo's a jerk. Anions always migrate towards the anode. Cations move to the cathode. The cell potential is a positive because Voltaic cells give off a voltage. When we calculate the cell potential, the potential difference, calculate the voltage, it's always a positive number. They give off electricity. Spontaneously, the oxidizing agent is always higher than the reducing agent in a Voltaic cell. Other things, electrons move through the wire, always from the anode to the cathode. Electrons are being lost at the anode and gained at the cathode. That's the direction they move through the wire. the mass of the anode, the solid metal in there on the anode, its mass will go down as it's getting oxidized. The concentration of any ions in that solution will go up. The opposite on the cathode side, the mass of the solid will go up as ions get reduced, and the concentration of the ions in solution will go down as they get reduced, become solids. Connected to Voltaic cell style questions are, we can be asked to change the reference half cell. This is where the 0 is in the data booklet. Hydrogen is the reference half cell as this table is set up. We can get asked, what would be the reduction potential? What are those numbers down the side of the table if the 0 was in a different spot? If we changed the reference half cell? All of the numbers will change, but the relative distances, the relative difference between any two lines of that table is a constant. The reduction potentials are affected, but it's important to note a change in the reference half cell does not affect the cell potential. The difference between any two lines is a constant. The voltage produced by a voltaic cell is not affected if we change where the reference is on the table. After all of that, we moved into electrolytic cells. Lots of things in common with voltaic cells. We're going to follow the 5-step method to determine the anode and cathode half reactions, to determine the net reaction, same process. Couple of other similarities are electrons always move from the anode to the cathode, anode to cathode, anode to cathode. Anions move to the anode, cations to the cathode. That's the same. What's different? Voltaic cells are spontaneous versus non-spontaneous in electrolytic. Here the cell potential is positive for voltaic cells. Here we get a negative voltage. When we calculate the cell potential, we're going to do the same subtraction. In voltaic cells, that's a positive. In electrolytic, it's a negative number. The fundamental point of what those different types of electrochemical cells do is also the opposite. Voltaic cells go from chemical potential energy to electricity. They produce a voltage. Electrolytic cells convert electricity into chemical potential energy. They require a voltage. We have to plug them in. On a diagram, we're going to see a power supply connected to an electrolytic cell, whereas voltaic cells will have a voltmeter. That's an important difference too. Finally here, it's really going to be common for us to encounter the word molten when we're working with electrolytic cells. Not always. If we have an aqueous solution, when we're making our list, we're going to put water in our list. If we have a molten salt, molten sodium chloride, molten potassium iodide, we're going to have ions. That ionic compound still dissociates when it's molten. However, we will not put water in our list. That's an important thing. We're probably dealing with oxidizing agents that are below water on here. And so if we accidentally introduce water, we're going to misinterpret the strongest oxidizing agent. We can take our work with electrolytic cells and turn it into stoichiometry, more often than not connected to electroplating. Okay? We have a new formula, Faraday's law, that's rolled into our work with stoichiometry. It's not quite the same as our earlier method. Okay? If a question mentions current and time, without mentioning mass, we're going to use Faraday's law. It's the current in amps multiplied by the time in seconds divided by Faraday's constant, 9.65 times 10 to the power of 4 coulombs per mole of electron. We can find the value for Faraday's constant in the data booklet on page 3. It's there with our specific heat capacities and the water autoionization constant. However, if the question is connected in one way or another to mass, that is a dead giveaway that we're going to do stoichiometry. Right at the start now, we have an important difference. Earlier on, we use the 5-step method to figure out the net ionic equation for our redox stoichiometry connected to titrations. When we're doing electrolytic stoichiometry, we just need one half reaction. It's probably the reduction of a metal cation into a solid metal. It doesn't have to be like that though, but we just need one half reaction. Then two options. Because it's about mass, we might be doing mass over molar mass. If the question gives us the current and the time, we're going to use our new formula, Faraday's law. Again, an important reminder, the time must be in seconds. Then we're going to multiply by R over G. One of the numbers has to be the electrons from the half reaction, and we're solving for the mass, the current, or the time. This is a really big unit. We have a really strong mixture of theoretical, non-calculating ideas, practical applications of the data booklet, interpreting spontaneity rules, theoretical work about Voltaic, electrolytic cells, and oxidation numbers, but also a little bit of math thrown in there. We revisited stoichiometry in a couple of different ways. We had this new calculation for the cell potential, the potential difference, the voltage. We have Faraday's law thrown into the mix. Okay. I would invite you to revisit some of the other videos in this unit. Good luck on your exams, and I hope that helps.